This is Math 31, an introduction to calculus. And we are starting into chapter 7, which looks at trig functions and derivatives of trig functions. Although today, we are not going to look at derivatives yet. Today our focus is on limits, where we have trig functions inside a limit. And so you'll see here, beneath the heading for 7.1, we want to find the limit as theta approaches 0 of sine theta over theta. Now, as we have discovered in the past, sometimes we have limits where the numerator and denominator are both approaching 0. So since theta is approaching 0, obviously the denominator is. But the numerator, remember, sine of 0 is also 0. So both numerator and denominator are approaching 0, but we can't find a common factor in order to cancel it out and evaluate what this limit is equal to. So we need to resort to another technique, and what we have suggested here for us is called the squeeze theorem. So here's how it works. As you look at this shape that you can see on the right side of your page, we have three shapes there. First of all, we have this big right angle triangle, and then we have inside that kind of a semicircle sector, and then inside that we have a smaller right triangle. So here we have that smallest triangle, and that corresponds to this triangle here. And then we have this medium sector, this curve there, so that's called a sector where one side is curved, and that's this shape here. And finally, we have this big right triangle, and that's what we have on the right side here, this big right triangle. And as we look at those areas, we can see that the yellow triangle is the smallest, the green sector is the middle-sized, and then the blue triangle is the largest. And as our angle theta gets smaller and smaller, these three areas will approach each other, but we'll always have this relationship that the yellow triangle is smallest, and the blue triangle is biggest, and the green sector is in the middle. So what we want to do is come up with an expression for the area of each of these shapes. So first of all, let's look at this yellow triangle. Area of a triangle is 1/2 base times height, and I'm going to choose the base to be the side is labeled there, and since my hypotenuse is 1, the cosine of this angle theta will be the adjacent over 1, so it's just this adjacent side, which is b. And similarly, the opposite side, h, opposite angle theta, will just be h over 1 will equal sine theta. So we have an expression in terms of theta to describe the base and the height. And so we'll write down an expression for the area in a little bit. But let's look at the right-hand triangle, because there as well we can think we have 1/2 base times height. This time our base is 1, and the height, well, I have the opposite side to the angle theta is h, and the adjacent side is 1, so tangent theta is opposite over adjacent, so that'll be h over 1. Oh, so h is equal to the tangent of theta. The middle sector is going to take a little bit more effort because we haven't calculated areas of sectors in the past. But here's what we will do. We'll look at the area of the sector And if we look at the area of the sector compared to the area of a full circle, we'll have a fraction of the full circle. And that fraction will have to equal the size of this sector angle theta compared to the central angle for a full circle, which is 360 degrees, or 2 pi radians. So I've set this up with radians. Area of a full circle is pi r squared, but my radius is 1. So it's just pi times 1 squared. So I have this equation giving me the relationship between area and theta, and the pi's will cancel out, and I end up with area is equal to theta over 2. So now that we have those relationships figured out, let's just fill in this middle area is theta over 2. This first area for the yellow triangle, that's going to be 1/2 sine theta cos theta. Sine theta is the height, cos theta is the base. And then for area 3, the blue triangle, the base is 1, the height is tan theta, so 1/2 tan theta will be an expression that represents that area. And we have these inequalities showing that 1/2 tan theta has to be the largest, greater than or equal to the sector area, which is theta over 2, where theta is in radians, keep that in mind, and that's greater than or equal to the area of the yellow triangle, 1/2 sine theta cos theta. Well, all of these have a half in them, so why don't I just multiply everything by 2, and this will cancel, that 2 will cancel, and this half will cancel if I multiply each of those by 2. Now, when I multiply an inequality by a positive number, the direction of the inequalities doesn't change. So this relationship is still the same, where I'll have sine theta cos theta, which is less than or equal to theta, which will be less than or equal to sine theta over cos theta, which is the quotient identity for tangent. So what's the point of all this? Well, remember way back here at the top, we were asked to figure out what is the limit as theta approaches 0 of sine theta over theta. So that's where we're going. We want to somehow in this middle blue section get a sine theta over theta and take its limit and have that squeezed in between the green values and the red values. So since I'm going to want the sine theta over theta, right now I have a theta. What if I took each of these terms and I divided out a sine theta? Then I can see some things will cancel out. Sine thetas cancel. And sine thetas here cancel as well. Which leaves me with cos theta is less than or equal to theta over sine theta, which is less than or equal to 1 over cos theta. Well, now I have a ratio between sine theta and theta, but it's upside down from what I'm looking for. So again, I'm looking for the theta, sine theta over theta. So what I'll do next is I'll take the reciprocal of each part. Now, what you've learned in the past is with an inequality, if you multiply or divide by a negative, the inequalities switch sign or switch direction. The same thing happens when we take reciprocals. So, for example, I know that 1/2 is less than or equal to 2. Well, it's actually less than, but the less than or equal to statement is still true. If I take the reciprocal of both sides, I get 2, and I get a 1/2. Is the relationship still less than or equal to? Nope. The relationship changed. So whenever we take the reciprocal with inequalities, the direction of the inequalities need to reverse. So that's what we're going to see in our next line. I'll take the reciprocal of cos theta, and now it's greater than or equal to. The reciprocal here will be sine theta over theta. And on the right side, the reciprocal of 1 over cos theta is cos theta. So now in the middle I have what I was looking for, the sine theta over theta. And our goal is to determine what happens as theta approaches 0. So we are going to take the limit of each of these expressions. Well, that central one, sine theta over theta, we know both numerator and denominator go to 0. We don't know what's happening. But as I look at the left side, as theta approaches 0, cos theta approaches 1. And so my left-hand limit, or my left limit here, is going to be equal to 1. Maybe I'll drag it all out. So here, this is 1, because as theta goes to 0, cos theta goes to 1. Same thing on the other side. As this theta goes to 0, cos theta goes to 1. So guess what the limit as theta approaches 0 of sine theta over theta must be? We've squeezed it in. So in this inequality, the left endpoint and the right endpoint are both at 1, which means sine theta over theta must also be 1 as theta approaches 0. This is how the squeeze theorem works. Get it? Squeeze theorem. We've squeezed that middle part in between other values, so there's no other option. This limit has to equal 1. Well, this is the key limit that we will use to determine many other limits of trig functions. So here on the next page, as with any limit, sometimes you can evaluate by simply substituting. So we'll try that. In some of the questions in your textbook, you'll be able to just plug in a value, evaluate, you're done. But other times, we may need to manipulate it until we can get a sine theta over theta and make use of that limit that we've just proven using the squeeze theorem. And what we just discovered and wrote on the previous page, that limit as theta approaches 0 of theta over sine theta is 1, just like, guess this is the one that we actually proved, but the reciprocal of 1 is still 1. So it doesn't matter if the theta is on top or if the sine theta is on the top. Let's look at a few examples. We want to determine these following limits. Well, I've assigned 3x. As x goes to 0, 3x also goes to 0, so sine of 3x goes to 0. And so does the denominator. But this limit is not equal to 1. Here's what we need to do. I'm going to rewrite this limit. But remember, the rule that we have is that the limit as theta approaches 0 of sine theta over theta is equal to 1. So here I'm saying that theta is equal to 3x. But I don't have a 3x in the denominator, so I don't have a sine theta over theta. But I can get a 3 in the denominator. I can multiply 3 times the x, but if I multiply it in the denominator, I have to also multiply it in the numerator. Because then I've just multiplied by 1. I haven't changed the actual value. So now I have sine theta over theta. That's equal to 1. But I still have the 3 out in front, so I'm going to factor that out in front of my limit. 3 times the limit. And you'll notice here that I changed this to a 3x. Typically I won't do this, but this is actually what's happening. We just often don't show it. So here I have my 3x, my 3x, my 3x. So I have as theta approaches 0 of sine theta over theta. All three of those should be identical. But often what we will do is we will just leave this as an x approaching 0. And we won't be picky about changing that one. So in all the future examples, I'm not going to change it. I'll just leave it as x approaching 0. So what's going to happen? I get 3 times 1, which is just 3. There's the value of my limit. As we work through these questions, pretty quickly you're going to see some shortcuts. I expect you to show all the steps and not take shortcuts, even though you'll fairly quickly figure out some of these limits. But it's still new. So we can't see it that quickly yet. Question number 2. I've separated out the sine 3x in the numerator and the sine 2x in the denominator. Why? Because I'm taking the sine of 3x, I want to have a 3x in my denominator. If I'm going to divide by 3x, I have to also multiply by 3x. And that's what I've done on the right side. Similarly, where I have the sine of 2x, I want to multiply it into the numerator, but I also have to divide it or multiply it into the denominator so that I haven't changed the overall value of my expression. Well, now I can see that here I have a sine theta over theta, and here I have a theta over sine theta. So both of those limits as x goes to 0, those are both going to go to 1, and then what I'm left with at the end is these x's cancel out, and I get 3/2 as the value of my limit. Now, here's what we didn't do, but some may be tempted to do. We didn't cancel out sines, cancel out x's, and get 3/2. We did not do that. That is not legal math. That is the answer, but that's not the rationale or the reasoning for us to get that answer. So be careful that you don't do that, even though that's going to be a shortcut to check your answers quickly. Question number 3. Ooh, there are no sine thetas in this. But hopefully, Math 30-1 is coming back to mind. You see the 1 minus cos theta and you think, ooh, with a conjugate, I can turn this into a sine theta. So our first step here will be to multiply by the conjugate 1 plus cos theta over 1 plus cos theta. That will make my numerator a 1 minus cos squared theta, which is a rearranged Pythagorean identity. That numerator will equal sine squared theta. And again, that strategy that we made use of in Math 30-1, where we expanded the numerator, because that's why we multiplied by the conjugate, we didn't expand the denominator, factored form is likely going to be more useful. And now I have a sine squared theta. Good. Well, if I do some rearranging here, sine squared theta is sine theta times sine theta. I have 1 theta as a factor in the denominator. And so this first part here, as theta approaches 0, sine theta over theta, that's going to go to 1. What happens to the next part? Well, this sine theta, as theta approaches 0, this whole thing goes to 0. What happens in the denominator? Oh, well, this cos theta, as theta approaches 0, this goes to 1. So my denominator is no longer 0. I'm not getting that problem of 0 over 0. I'm getting 0 over 2. What is 0 over 2? It is just 0. Question number 4. Again, because I have that sine squared, I'm going to write that as 2 separate sine functions, and they're both operating on 3t. I have t squared in the denominator, so I can get a t underneath each of those sine 3t's. But I need a 3 in the denominator of that first rational expression. Well, not rational, but that expression. And I'm going to need a 3 in the denominator of the second one as well. So what do I get? This part goes to 1. That will also go to 1. And then I have a 3 times 3, which is 9. There is my limit. And those are all the examples. Next up, there's a page of check your understanding questions. So why don't you pause the video at this point and take a look at the 5 check your understanding questions on the next page. Question number 9 is tricky. We haven't seen anything like that yet. Do what you can with it, but when you're ready to look through these, then restart the video. So pause the video now, restart it once you've tried these questions on your own. Number 5, there's my work, very similar to some of the examples we already did. Number 6 is a little bit different. Because I have that subtraction in the numerator, I can write it as 2 separate fractions with the common denominator of x cos x. Then the process is similar to questions that we previously looked at. On to question number 7. This time I could see a common factor of t in the denominator, so I pulled that out, kept it underneath the sine 4t, and then multiplied and divided by 4. And as t goes to 0, this whole thing goes to 0, so I get 4 over 1, which is just 4. And then question 8 is similar to one of the examples we did where we'll multiply by the conjugate. And I end up with a limit that's equal to 2. Well, this leads us to question number 9. Number 9, what? X isn't approaching 0? How in the world are we supposed to find this limit? Well, x may not be approaching 0, but if x is approaching negative pi, x plus pi is approaching 0. So I treated it almost like an equation where we had that approaching arrow. So if we have x equal to negative pi, I could rearrange it to say, oh, x plus pi must equal 0. We don't have an equation, but we can actually treat it similar to an equation, where if x is approaching negative pi, then, well, if this is approaching negative pi plus pi must be approaching 0. So it's also a true statement. So that's the first step. If you have an idea now, pause the video, see where it takes you. Otherwise, I'll just keep going. Well, there's my theta, there's my theta. This is not my theta. So there's a problem with what I have inside that sine function. But on your formula sheet, you have an entire side that gives you trig identities. And if you look at those trig identities on your formula sheet, and you look at the related angle identities, you will find this identity, that the sine of pi plus x is equal to negative sine x. So if I rearrange that, I can discover that sine x is equal to the negative of sine of x plus pi. So I can do a substitution. And since sine x equals all of this, I can replace this sine x with a negative sine of x plus pi. And that's what I've done here. Now maybe you want to pause the video and finish this off. But I'm going to keep going. We've gotten to this point where this is my theta, there's my theta, there's my theta. All three are the same. So I have the limit as theta approaches 0 of some stuff times sine theta over theta. Well, let me erase those again. What's going to happen? Well, there's that part. The limit as theta approaches 0 of sine theta over theta. But I'm missing the negative and the x squared. So using those rules for limits way back on, I think it was page 13, I can write this with the limit. And now I've switched back to the original question where I have x approaching negative pi. And it's operating on the negative x squared. Well, the first limit, we know, is equal to 1. The second limit, as x approaches negative pi, I'll have a negative pi being squared and taking the negative of that. So my answer, negative pi squared. There you have it. Limits of trig functions.